Hello and welcome to Eyes on Research, the podcast that digests the latest scientific innovations in eye research using simple and understandable terms. I am your host, Thales Guimaraes, medical doctor and clinician scientist at Moorfields Eye Hospital. Hello, my friends, and welcome to another episode of Eyes on Research. I hope you have been well and the week has been treating you well so far. It's a great pleasure to have you here with me today. And in today's episode, we'll be talking all about color vision deficiency, which is also called popularly as color blindness. But before we get there, I walk you through how we developed color vision, how it works, and we also talk about vision in general, how we see things. And actually, let's start there. The first question that we have to ask is how is it that we can see things? And very simplistically, the beams of light come inside our eyes, passing through the whole media of the eye and reaching the retina, which is this film like tissue that is composed of many millions of light sensitive cells. These cells are what we call photoreceptors, and they process the photons of light and generate a cascade of events that ends up with electrical activity being sent to the brain via a nerve that is called the optic nerve. And this nerve is like a straw that's connecting the retina to the brain. Now, we have two different types of photoreceptor cells, the rods and the cones. The ones that give us color vision are the cones, right? Essentially, we have three types of cone photoreceptors in the retina, which are fine tuned to different wavelengths. The cones have three types of pigment proteins that we call opsins, and these have different spectral sensitivities, namely the short, the medium, and the long wavelengths. So the blue, the green, and the red. And the typical healthy human eye will respond to wavelengths from about 400 nanometers all the way to 750 nanometers. So from violet in the shorter spectrum all the way to deep red in the longer spectrum with a sensitivity peak at around 555 nanometers. Wavelengths shorter or longer than this range are called ultraviolet and infrared, respectively. But we as humans, we cannot see these wavelengths. Now, color vision is an integral part of the human visual system, right? But it's not only seen in humans. In fact, one of the most acceptable hypotheses is that color vision evolved in primates, our tree dwelling ancestors. They developed color vision because they were under a high evolutionary pressure to develop the ability to see different colors. This is because primates who were able to see colors had a huge evolutionary advantage. Think about this for a second. The primates who were able to see the colors would be able to see the bright colored ripe fruits, which, particularly in the tropics, have a very bright colored hue. So, this conferred them a huge evolutionary advantage as it increased their survivability. One thing that's important to say here is that colors are not an actual inherent property of material, of matter, right? Color perception is related to the light that the object does not absorb and instead reflects. Without light, we don't see colors. We have discussed how we see things, how we developed color vision, and how it kind of works. Now let's talk about color blindness, right? The purpose of this episode. So, first things first, if someone has color vision deficiency due to a genetic cause, usually their color vision won't change. So, it won't get better or you won't get worse over time. It's mainly stable. Although you can also get color vision later in color vision deficiency later in life, right? If you have a disease or injury that affects your brain or your eyes. For example, things that come to mind right now are diseases like age-related macular degeneration, which by the way, we do have an episode from a few weeks ago, so go check it out. Neurodegenerative conditions like multiple sclerosis, things like Parkinson's disease, things like Alzheimer's, and traumatic brain injuries. Some medicines can even cause color vision deficiency. One example is digoxin, which is a medication I use for the heart. So even medications can cause color vision deficiency. But let's focus a bit on the genetic causes. All of these pigments, or in other words, these opsins, are proteins that are encoded by different genes. And the way that I tell my patients to think about this is to trace a parallel. Genes are like a set of cake recipes. Our body needs the instructions on these recipes to be able to make a cake essentially. And the cake on this case being color vision. The genes for medium and long wavelength proteins are both in the X chromosome. In fact, the most common type of color vision deficiency is named X linked red green color vision deficiency. The prevalence of this in the population varies according to the ethnicity, but it's averaged to be around 4 to 8% of men being affected. So that's indeed quite common. We're talking about 4 to 8 in 100 men, right? And we say that this is an X linked trait because it's linked to the X chromosome, which is a sex chromosome. For someone to have this condition, all of the X chromosomes must carry mutations on the gene for red green color deficiency. While females have two X chromosomes, male only have one X and one Y chromosome. Typically, only males are affected, right? They only have one X chromosome, so if they inherit the gene for red green color deficiency from their mother, they will become affected and have the red green color vision deficiency. On the other hand, females have two X chromosomes, one coming from each parent. For females to inherit red green color vision deficiency, they must carry the gene for the condition in both X chromosomes, and this is an extremely rare event. And by the way, the most accurate term is indeed color vision deficiency because despite a few rare instances, patients are not blind to color and can actually differentiate a few shades of colors. So, on the same page, let's talk about the types of color vision deficiency. And we classify these traits according to the wavelength or according to the opsin that's being affected. So, you will have heard me saying many times in this episode now red green color vision deficiency. So, let's start there because it's the most common. There are actually a few types of red green color vision deficiency. One patient can have deuteranomaly, which is when it's the most common one of those. And it's when patients have a hard time to differentiate certain shades of green from red. So that means that certain shades of green look more red. Then you also have protanomaly, which is when certain shades of red look green. And these two are milder. You have the more severe forms, which are named deuteranopia and protanopia. Essentially, patients are unable to differentiate red and green in any of those. Then you also have the blue yellow type of color vision deficiency, and that's way less common. Tritanomaly, and then you also have tritanopia. When you have the treat anomaly, just like for red green color vision deficiency, that's the milder form of those. So you have a hard time to differentiate between blue and green and yellow and red. You have tritanopia, not only the colors look less bright, but you are also unable to differentiate blue and green, purple and red, and yellow and pink. Now, there are even more severe types of color vision deficiency. One of those is complete color vision deficiency. So patients affected with this can't see colors at all. It's also called rod monochromacy because only the rods are working properly, or achromatopsia, meaning essentially can't see colors. It's rare and it's associated with other symptoms such as very intense sensitivity to light, unusual back and forth eye movements, and reduced central vision. Now, we have a full episode on achromatopsia. It's a relatively common condition in the genetic world, right? But isolated, it is rare. So go check it out as this will make a little bit more sense. We talk about it in detail there. You also can have other forms of color vision deficiency, like for example, when only the blue cones work. It's named blue cone monochromacy. It's very atypical. It's a disorder also linked to the X chromosome, and that's when the red and the green cones do not work properly. Both of them do not work properly, so patients can only have the blue cones working. Now, treatment wise, there have been indeed several clinical trials using gene therapy technology for two types of the more severe form of color blindness named achromatopsia. In summary, the treatments are safe, but they are lacking a bit in efficacy for a variety of reasons. We discussed the results in a bit more detail in a specific podcast episode that I have just mentioned on achromatopsia, so go check it out if that's something that interests you. But what about for the milder forms of color vision deficiency? What about for the mild form of red green color vision deficiency, for example? Has there been any clinical trials for that? And the answer is no. By the way, would any patient actually want to be treated? In most forms of color vision deficiency, actually, in the overwhelming majority of those, patients have a normal life. And I'm not saying that they don't have symptoms, they do, right? They may have a hard time to drive sometimes because they may have a hard time to differentiate the red and the green light, right? But when we think of treatments such as gene therapy, for example, they usually involve a relatively big surgery that carries its own risks. And as doctors, we need to first do no harm to the patients. So, do the risks outweigh the benefits? I don't know, but I would say possibly the risks far outweigh the benefits on this case. Let me know what you think. We have a new feature in this podcast which allows you to send me a direct message. It's on the description, so feel free to drop me a message with your thoughts. I would love to hear from you. And what about the colorblind glasses, like the ones made by the company Enchroma? Do this work? And you may have seen the videos, right, where they give these glasses for the first time to people who are colorblind. So, just to clarify a bit, these glasses do not modify in any way a person's photoreceptors, right? It doesn't modify the light sensitive cells. These are just glasses, but they do change what the people who wear them see. And they enhance the distinction between red and green, for instance. What happens in these glasses is that um, some light that's coming through the glasses are actually blocked so that the red and the green wavelength, which are the long and the medium wavelength respectively, do not overlap as much. That's a really cool concept. So in some ways it works like a restrictive filter. They may, however, worsen night vision while you're wearing them, so it's not a good idea. It's not recommended to wear them at night. And they are also expensive, right? Which is another of the caveats. They may not provide the type of experience you're hoping for. I have read some mixed opinions online, although I have personally read many reports from patients themselves saying that it did help them differentiate a few types of colors. So it's a very cool concept. Let's wrap this up and not make this any longer than it should. Thank you so much for listening to me today. I hope you found this episode useful and that some of the things that we have discussed can enrich your knowledge. I should also say that we have social media accounts where we post short videos all the time. So visit us on at Eyes on Research on your favorite social media, Twitter, Instagram, LinkedIn. We have it all. So go look for us. Also, you find a link in the description of this episode to our Buy Me a Coffee website, which is the website that we use to post our articles. Please consider subscribing to us there. It's completely free, and we're using that as a blog. So you see weekly posts about curiosities and trivia on eyes and vision, as well as hot research updates that did not go on to become a full episode. So do consider subscribing. You need to click the three dots in the top right corner of the website and provide your email and hit follow. Thank you very much, and I hope you have a wonderful rest of the week. And I'll see you in the next episode. Bye bye.